Good afternoon, everyone, and welcome to the summer series presented by the Montana Renewable Energy Association. My name is Andrew Valinas, and I am the Executive Director of MREA. Before we begin, I'd like to recognize our sponsors, Clearwater Credit Union, Kaufman Engineers, the Montana Energy Office, Onsite Energy, Aero, and Ford Montana Foundation. And I'd also just like to start by describing MREA for those who don't know. MREA is a nonprofit organization that works statewide to educate and advocate for renewable energy. We work on policy, we work on education programs like this, we host community events, and we are one of the leading voices for renewable energy in Montana. Today's topic is microhydro systems. I'm really excited about this topic. My background is in a little bit of hydro work, or at least my education was. And I think it's a lesser used type of system, at least microhydro is, in Montana, but it's a really interesting type of system. So with us is Rip Hamilton from Solar Plexus, and Rip is on the line live for the Q&A session. What we wanted to do was take a virtual tour, a live tour of one of these systems, but with everything going on these days, doing a live presentation and taking care of social distancing requirements is a little challenging. So what we did was we pre-recorded a site visit, and what I'm going to do is share that video with you all. It's about 15 minutes long, and when it's done, we'll go ahead and jump into the Q&A. Hi, everybody. My name is Andrew Valinas. I'm the Executive Director of the Montana Renewable Energy Association. Welcome to beautiful Gold Creek. We will be talking today about microhydro systems, one of which is housed right behind us in this little shed. I want to introduce our guest speaker today, Mr. Rip Hamilton from Solar Plexus. Thanks for joining us, Rip.
Thank you.
Rip and I are going to be talking about microhydro systems, the different components, different considerations, what to think about as far as where the water's coming from, and really everything you need to know about these systems here in Montana. So Rip, why don't we start by you just telling us a little bit about yourself and your work.
Yeah, my name is Rip Hamilton with Solar Plexus. We're a renewable energy company, been in business for about 26 years, and actually started doing microhydro. So, obviously there's not a lot of streams and microhydro sites in Montana, so we branched out, cover about 7 states with hydro projects, and actually had to go into solar a little bit because there wasn't enough hydro around. So hydro's our favorite, but we do a lot of solar too.
Great. Well, I'm glad it's your favorite because that's exactly what we're talking about today. Before we dive into the system components, Rip, can you tell us a little bit about maybe some of the initial considerations people should be thinking through before they want to invest in a microhydro system?
Yeah, so a lot of clients will call, especially this time of year in the spring when we have high water. Everyone's seeing water running down every drainage there is, and they want to jump on and put a hydro system in. The main consideration is how much water does that drainage flow in the off season. So we usually tell them to take some measurements and come back in August, September, October, and take some measurements with the same devices they were using, whether it's damming up the stream, putting a small pipe in, using a 5-gallon bucket and timing it, or if it's at a culvert at a road crossing, you can get a pretty good idea of what the flow is. But the flow rates are so variable that it's critical that you get good measurement during the low flow time of year. That's going to be the baseline for how much power we can produce. The other critical element is the head. So the vertical distance from where you can take the water out on a piece of property to where you have to return it to the stream. And that elevation is the other important factor. And there's some other critical things, distance the pipeline runs, and wire loss from where the turbine is to your point of use, but those are less critical and easier to overcome than the head and flow rates.
So the head and the flow rate seems like those are really what you calculate to generate the power, and a lot of those it sounds like you can do kind of DIY measure at home with the help of maybe your installer.
What about other considerations like electricity use for the home? Is that something you go over typically with the user?
Yeah, we can. So, given a resource of water, the amount of water and the drop, we can calculate how much power you can produce, and more or less tell you what your limitation is on power before you're going to have to augment with a generator or with another source, wind or solar. So, establishing that baseline and letting the client know that anything above and beyond that is going to have to be supplemented.
So Rip, one of the considerations obviously for microhydro is you have to have water on your property, and water rights are an important issue. Can you talk to us a little bit about how some of those considerations?
Yeah, so if the water is originating on your property and it's a spring, then the water rights process is relatively easy, meaning about a year process. If you have an irrigation right or an existing water right on the property, you can sometimes get it converted to a hydropower non-consumptive right. That process usually takes a little bit longer. If you have no water right at all, then you have to make sure that the water basin you're in is open to new water right applications. And then you would also want to consider where you are in line with other people's water right to make sure that you can maintain that flow throughout the year.
And where can people go to find out more information about water rights?
The DNRC is the best place to check, and you can find out where your property boundaries are, geocode or whatever, and then contact them to see if the basin's open or not.
Great. So microhydro systems and their design can be really specific to the site that you're on. So Rip, can you tell us a little bit about this site and some of the intricacies of how you designed the system?
Yeah, so this site is pretty unique in that it has a nice groundwater spring on site. We were able to capture the water underground, so we don't have any filtration. We don't have to worry about leaves in the fall or anything like that. Everything's nice and clean year-round. And then the water travels 1,400 feet down a pipeline with about 120 vertical feet of drop on it, and supplies the turbine behind us here in this powerhouse. Other sites, we've installed catch basins with different types of screen. Some have slotted well screen, and others have it's called Coanda screen. It's a wedge wire that's fish friendly, and there are some Fish, Wildlife, and Parks has some rotating screens that they sometimes use. We've used those in Idaho. So there's a variety of options for pulling the water out and still protecting fish if there are fish in the stream.
And some of that I imagine will depend on, like we said, this is a ground source system. Some of the systems are surface water, right? Meaning probably what people are more used to thinking about when they think about hydro, which is water flowing down a creek or a stream.
Right. So when you are installing a system on a stream, the diversion has to be set up so you can let some of the flow go by to satisfy low flow requirements for fish during the wintertime, or if there's people with irrigation rights downstream from your head gate. So designing that intake is fairly critical, and it can be a fairly expensive part of the project.
So Rip, talking about the size of these microhydro systems, about what size are we looking at with this system, and what might somebody, maybe a typical customer, need to help produce enough energy to cover their home energy loads?
Yeah, so this system has about 1,400 feet of lineal pipe, 120 feet ahead, and we're running in the neighborhood of 100 gallons a minute, and we're generating about 600 watts continuous. So the average Northwestern Energy home uses about 1,000 continuous, but that includes a lot of heating load. So if you take away hot water heating, your dryer, maybe some range, and you run all that on propane, 600 watts is more than enough to run the house 24/7. So we're supplying a battery bank, and in this case, a fairly small battery bank, about 24 volts at 370 amp hours, is a tiny bank for the house this size. And it's pretty amazing, and it's simply because those kilowatt hours are replaced every night, and with the systems running 24/7.
And you talking about one of the benefits of hydro versus solar, for example, or wind, depending on the water source that you have, hydro can run 24 hours a day,
Right.
7 days a week, and the flow might change obviously throughout the year. We talked about a high flow season and a low flow season, but it's pretty regular power coming through, right?
Right. So we're getting 600 watts, and even if we had a really dry year and we had to shut a nozzle off, and maybe we were down to 400, you wouldn't be able to run this house on a 400 watt solar array simply because you're down to 1.9 hours of full equivalent sun here, and averaging about 4.4, whereas the hydro is 24/7.
Great. And yeah, one of the very interesting and many benefits of hydro.
Yes.
Obviously has its other trade-offs for sure, but that's one of the great things about it.
So the water comes in and we hit this gate valve. That gives us the option to shut the whole pipeline off if we need to do any service work on the turbine. And then we have a second valve for irrigation and firefighting, a third valve to drain the system. If we shut the pipeline off up above, we can drain the whole system out the drain here without running the water through the nozzles. This valve shuts off all the nozzles to the turbine. This is a 4 nozzle turbine, so we have 1, 2, 3, 4. Right now we have 2 nozzles on, 1 and 2, 3 and 4 are shut off. The water comes in, goes through the Pelton wheel, hits the Pelton wheel and spins it, turning the generator, creating the electrons. The water then drops out the bottom into this basin and then follows the drain pipe back to the stream. The electrons would go out to the combiner box where we're monitoring battery voltage and feeding power up to the house. And in this particular case, everything's 24 volt DC. We're watching the battery voltage with these 2 controllers. These are diversion load control. So when the battery voltage climbs up to a point where the batteries are going to become damaged due to overcharge, these heater loads will kick on and drag the battery voltage back down. The unique thing with a hydro system is that it always has to be on. It's not like a solar system where you can shut it off. So this always has to have a load on it. Therefore, these heater loads are critical to the operation of the system. This particular structure is nice because it just lays over. If we have to service it, we got plenty of room to work in here and access everything. Some people will sink these in a concrete vault. A little tougher, it's a little confined, but this is a really nice setup, the way this is laid out.
So Rip, we just looked at the Microhydro system from the outside, the one that's hooked up and running. This is one of the internal components. Can you tell us a little bit about what this is and how it works?
Yeah, so this is an actual scaled down version of what we just looked at. This is the ES&D mini turbine. So in this case, it's a 1 nozzle turbine. The water would come in, and the pressure of the water would hit the Pelton wheel, and when it comes into contact with the spoons, it rotates it, and that rotation turns the generator, which creates the electricity. Then in the case of down below, we'd have the discharge below it with a pipe coming out. So this is the Pelton wheel or the turgo wheel part of the turbine, depending on the brand.
And like you said, this one is scaled down. This is 1 input, right? Whereas the one that we just looked at had 4 different inputs for the water.
This turbine would work best with low flow, really high head. So maybe head elevations of maybe 300 feet and a flow rate of probably 10 gallons a minute, 15 gallons a minute.
Okay, Rip, so we've walked through the system, we've looked at the different components. Say we're a homeowner and the system is installed and it's producing energy for us. What are some of the next steps that we need to think about? Is there data monitoring? Is there maintenance required? Can you walk us through some of those things?
Yeah, so when we install the systems, we typically install a voltage meter, an amp meter, so we can monitor what is going on at the turbine itself. And then obviously the voltage will vary depending on battery use, but it's amps times volts equals watts. So you can multiply the 2 together quickly, come up with a number, and know whether the turbine's operating properly. You need to watch and make sure that the screen on the intake is cleared. In this case, again, it's unique and that everything's underground and super maintenance free, and maintenance free is always good. Every 2 or 3 years, you may have to change bearings depending on how hard the turbine is running. This 4 nozzle turbine is a little bit overkill on this site and would produce about 1,000 watts under ideal conditions. The homeowner doesn't need that much, so they've closed 2 of the turbine nozzles and operate closer to their needs. Still overproducing, but not overproducing so much that the turbine is getting a bunch of unnecessary wear and tear. So turbine bearings, cleaning the screens, and just general inspection of everything occasionally is all helpful.
Great. And then at that point, you're just producing some nice, clean, homegrown energy.
Yep.
Excellent.
24/7.
Well, Rip, thank you so much for joining us today and for sharing your expertise. And thank you for tuning into our video. The Montana Renewable Energy Association has lots more information on our website at montanarenewables.org. We hope you will check it out, and we hope you'll tune in to another one of our educational videos in the future.
Well, Rip, thanks again for joining us and putting together that video. I know I had a really fun time doing that. A couple questions have started rolling in, so I want to mention to folks, if you have any questions, please start to send those in via the chat function, and I'll go ahead and pass them along to Rip. Rip, to begin with, though, I actually had one because during our presentation, we didn't really get a chance. We talked a lot about screens and how those might be important, especially for a surface water source, and just wanted to ask, we've got a photo here, ask you to talk a little bit about different types of screens that might be used and some of those considerations.
Yeah, so this is the Coanda or wedge wire screen that I briefly spoke about. This is the most common one that we use. And essentially it's a self-cleaning screen. So you set it up, damming up the stream basically, and having the spillway be the entry to the pipeline. So as the water spills over that wedge wire, it basically shaves it off. The wedge wire's welded in such a way that it acts almost like a cheese grater and just slices the water off. The excess water keeps the leaves and debris from building up on the screen, and but the water will drop into the basin. So under that screen, there's about a 2-foot basin that the water falls into with the pipeline coming out of the bottom of it. And it's a good way to keep the water moving through, keep the screen clean, and if there are fish in the stream, these are fish friendly.
Great, and thank you for sharing that. I know, obviously, like we mentioned in the video, and like you talked about, there are a number of different kinds, right? And you know, one might work better than another depending on your situation. I think that was something that really stood out to me, especially because, you know, you and I and kind of our MREA community, we talk so much about solar, but the design of these microhydro systems seem to be pretty hyper specific to the location that you're working with, right? I mean, there's so many more considerations other than just, you know, where's the sun shining the best.
Yeah, there's none of these systems happen quick. These are all systems that take generally several years to develop and get all the permitting on, and so from the time that people call till the time the project's actually completed is, you know, if it's a year, that's super fast. So yeah, a lot of design criteria that you got to review, dealing with, you know, how to dam up the stream and you know, be somewhat responsible about making a huge mess and getting all the permits in order. And almost all these streams are fish barren. We've done a couple streams that have bull trout spawning in them, and we've got the blessings from the FWP on installing those systems. But it's a process, and you got to be pretty careful with it.
Sure. Well, thank you again for again shooting that video with us. Let's go ahead and dive into some of the questions from the audience. The first one here is, Rip, can you talk a little bit about what happens in the winter time when water freezes?
Yeah, so obviously on the site that we looked at, it's not an issue because the intake's all underground, but on the Coanda screen shot that we just saw there, the winter is actually the least maintenance time of year because the ice will freeze over the entire intake and the water will continue to flow underneath the ice. And no, there's very, very little debris that will come down and plug up the screen at that time. So winters are usually the most maintenance free point. The worst time of year is in the fall when the leaves are really thick. And in some cases, if you have a lot of large trees, the large needles will sometimes mess with the wedge wire screen. And the other time that's a little tough is spring runoff, where you'll have a lot of silt and stuff going through that is almost impossible to filter out. And so when the silt goes through the turbine, it can be fairly abrasive and sometimes cause some wear and tear on the Pelton wheel and on the nozzles.
Well, that's a pretty amazing segue right into our next question, which is actually a question about mineral buildup on the turbine or other components from the water, and how that might be addressed or kind of what to do there. Is that just kind of a regular maintenance issue, or is that something that you might need to go in and scoop out some gunk or something like that?
So most of the turbines we do not have a lot of mineral issues with. We do have a few sites that are on warm springs. Those areas or those sites do have quite a bit of mineral buildup, and we usually end up replacing the bearings more often on those sites. We can get Pelton and Turgle wheel runners, we can have them fabricated bronze or stainless steel or plastic. So we have some options. We usually on the hot spring sites we'll get a chemical, basically the chemical test for what's in the water on those locations. Then we'll run that by our turbine manufacturers and see what they recommend for the type of runner to use to get the most life out of the system. We've had, on most of those sites, we've used bronze runners and we've had pretty good luck with those, but we do end up changing the bearings more often.
Great. Let's see, the next question here, did I understand it correctly that propane is used for load balancing? So yeah, we didn't necessarily talk about that maybe much in detail, the other components of this particular system that we did with the video, but it is an off-grid system. So they have hydro, they have a small solar array, and then there is some, I think some propane backing things up. Is that right?
Yeah, they have, and most of those sites would have, you'd have the turbine or generator, hydro generator, and then in an off-grid situation, you'd have some sort of backup propane generator or gasoline generator, depending on the fuel available at the site. And in some cases, a solar array of some sort to help augment. So in some cases, the water rights are only irrigation rights. So in the non-irrigation season, the ditches will be shut off, and then you're back on solar. So depending on the site, but some type of hybrid generating source is almost always there.
Yeah, and I think that goes back to something we talked about earlier, right? Which is just with the microhydro, there are so many other considerations that, it's really, really very site specific, which I imagine.
Yeah, in the case of the site that we were on there, Matt said that I don't think they've run their backup generator since they put the hydro in. I think he said it's basically
right
set there. So yeah.
Yeah, I recall him saying that as well. Well, you mentioned irrigation. The next question we had is, can you discuss microhydro and irrigation canals? There's a large canal here in the county that the person is in, and it has many offshoot canals. In the fall, it doesn't run, but would it be practical to do microhydro to generate electricity for barns and houses, maybe when those canals do run?
Yeah, it can, depending on the site, if you can generate enough power and you can get an agreement with the utility, or the co-op to overproduce during those irrigation times of year, overproduce enough to offset, a substantial amount of your consumption on a net yearly basis, then it can be worth looking at. We've seen some sites where they try to develop them as a QF during the irrigation season. That's pretty tough. I guess if there was enough, if you could generate enough, it might be worth it. But by the time you pay the insurance and go through all the costs of intertying with the utility and everything, we haven't seen many of those come through.
Yeah. Man, you're doing a really good job segueing between these questions without even knowing it, Rip. The next question we had is, have you done an analysis on length of time for return on investment for some of these systems? I think people, when we talk about solar, like we do so often, there's a lot of discussion about payback times. What are some of the practicalities of payback times for something like Microhydro?
Yeah, the payback on most of the hydro systems that we install that are off grid are almost immediate, because bringing in the utility just isn't an option. The cost of doing that is usually prohibitive. If you're looking at net metering, your paybacks are probably 3 to 4 times faster than a solar array of equivalent size, simply because it's operating 24 hours a day. The upfront costs are a little bit more, but it depends on the site. And if you have a good site, it can have a pretty quick return on investment.
Great. Here's a technical question for you. Do you recall the diameter of that 1,400-foot pipe that was used at the location that we shot the video?
Yeah, that was all 4-inch HDPE poly pipe that we welded on site and pulled in.
Gotcha. Let's see. Next question. Do you know about how many microhydro sites there are in Montana? Are they all privately owned? And how old is the oldest continually operating system?
Oh boy.
I think this is our trivia style.
There's a lot of them. My stepdad, Lee Tavner, built his in 86, 87. There were probably at least a half a dozen that came online about that time that were privately held as qualifying facilities. I don't know how many we've installed. I would guess somewhere around 50. The oldest ones must be utility owned. There's a lot of those that are still operating. Mission Valley Power has a few pretty old ones up there. Yeah, I'm not sure. We see old relics of them all the time. Gibson Reservoir has a ancient one that's still operating at the headwaters of it. It's not on the reservoir itself. It's on a tributary on a guest ranch up there. It's been operating for years. We were just up there the other day to service it, and just keeps plugging along. So there's a lot of them around.
Yeah, I think as far as hydro goes, I think the oldest, this isn't Microhydro, but I think the oldest dam in the state, excuse me, is the Madison Dam, and that was built in 1906. So, hydro in Montana has been around for a while, but as far as Microhydro, I think we've seen just a little less of it. But, it's certainly growing, I would say.
Yep. Yeah.
Great. Well, we are pretty precisely at the top of the hour, and it looks like we have naturally run out of questions from the audience. So I think in the interest of time, we'll go ahead and end the presentation for today. But Rip, thank you again so much. And thank you everyone for tuning in. Thank you to our sponsors, of course, as well. And a reminder that the summer series continues next week and all the way through until September. Next week, our presentation is going to be on off-grid storage systems. It's our last of our 3 videos that we shot, and we're going to be talking about solar with battery storage off-grid. Really interesting topic, and looking forward to showing you all that video again. So thank you again to Rip and to all of you, and we hope to see you again next week. Have a great day.
Thanks, Andrew.